Okay, in this video we're going to take a look at radicals. So let's start with a few definitions. Obviously we need to have a symbol for radicals. Then we have two other important parts of the radical, the part that's inside the radical symbol, which is known as the radicand, and the part that's in front is kind of like a superscript notation, which is known as the index or the order. And there are some restrictions. The index has to be greater than 1, and it has to be a natural number, so 2, 3, 4, 5, 6, 7, 8, and the radicand has to be a real number. If this is true, then there are a few things that happen because of that. So let's take a look at those. First of all, if the radicand is greater than 0 and the index is even, then we have the nth root of a. So for example, we could have the square root of 25, we can calculate that, we can have the 4th root of 16, we can calculate that, we can have the 6th root of 200, we could probably get a calculator to calculate that for us, etc., etc. So the a value is bigger than 0, and the index is an even number. Another option that we can have is a can be less than 0. And if a is less than 0 and n is even, then taking the nth root of a just doesn't exist. For example, trying to take the square root of negative 16 does not exist, and at least it doesn't exist in the real number system. However, if a is less than 0 and n is odd, then you can take the nth root of a. In fact, it doesn't even matter if a is less than 0. If n is odd, then you can take the nth root of a, so you can take it for positive numbers, and you can take it for negative numbers. Not a problem. One other definition is the nth root of 0 is always equal to 0. Now let's just take a quick look at solving some exponential equations, and to do that using radicals. Most of this should probably be review from past years, but I'll try and zip through some of it. If you have x squared is equal to 4, when you take the square root of each side, you get plus or minus the square root of 4, which is plus or minus 2. When you have a 4th root, similar things happen. You take the 4th root on this side and you take the 4th root on this side, and you get the 4th root of 10. And if you have a calculator or are extremely good at math, you can figure out that this is approximately 1.778. And if you have something a little bit more complicated, you can get rid of coefficients first. Minus 51 divided by 3 is negative 17. Take the 5th root, and when you take the 5th root, you don't produce two solutions. You only produce one. The 5th root of negative 17 is the exact answer, and that's approximately negative 1.762. Okay, we're going to switch gears here now and take a look and see what happens when we graph radicals, or when we apply a radical to a function that we already know. A little bit of Unit 1, the transformations unit, coming into this as well. So our basic radical graph, y equals the square root of x, I'll just sketch it. It looks like this, basically like a sideways parabola. So we've got our y and our x, and this function has a domain of x has to be greater than or equal to 0, and then it can be anything, and the range is the same. Y's have to be greater than or equal to 0. And that's because it's a square root graph that I'm doing. In a little bit we'll take a look at what happens with cube root graphs and taking functions and applying the square root function or the cube root function or an nth root function to it. One of the key ideas is that it really changes the graph because it has a much more restricted domain and therefore can have a much more restricted range. But let's just focus on this one for a second and think about what happens with these transformations. So what happens if I try to graph y equals negative the square root of x. Well, negative the square root of x is the negative sign is doing a reflection across the x-axis, and so you get a graph that looks like this. If instead of that I do y equals the square root of negative x, that does a reflection over the y-axis, because x has been replaced with negative x in our original graph, and so I get a graph that goes in this direction. What happens if I do both? Well, I get a reflection over the x-axis and a reflection over the y-axis, and I get a graph that first of all reflects and then reflects again, and ends up in quadrant number 3 looking like this. If instead of doing reflections, what happens if I start doing some compressions and expansions? Well, same things that we saw in the transformations section. If I have y equals 2 root x, I am doubling all the y values, and my graph goes like this. So this value is now doubled. It's not the best scale, but those values are all doubled. If I graph y equals the square root of 2x, x got replaced with 2x, so all my x values are half as big. And so these points move this direction, and so I get a graph that looks like this. It is different than 2 root x, which doubles in this direction by quite a bit. And those graphs are both different than y equals 1/2 root x, which takes this graph and compresses it, makes it look like this. And those are again different than y equals square root half of an x, which takes this graph and expands it this way and would look something like this. Putting all of this together gives us this equation, which also includes the translations left, right, up, and down. And you should be able to sketch something like y equals negative 2 3x minus 3 plus 4 from the basic graph. Don't forget to factor this part. In fact, maybe grab a piece of graph paper right now, pause the video, go see if you can remember how to graph this by hand, and then double check it on your graphing calculator. In fact, maybe I'll check that as my check-in with you to see if you've watched the video and got to this part and done a little bit of an exercise. Okay, I also want to take a quick look at what will happen with a cube root graph. What if you apply these graphs to functions that you already know? And the main part with that is that when you apply these square root graphs to any kind of function, with a cube root graph, of course, now we can put in negative values, so your domain can actually be anything. Whereas when you take square roots, your domain has to be bigger than or equal to 0. At least f of x has to be bigger than or equal to 0. So your domain gets restricted in some way because you can't take square roots of negatives. And of course, when you extend it to here, then you need to know whether or not your n is even, in which case this is true, or if n is odd, in which case this is true. And the easiest way to go about graphing something more complicated like these last two is to make up a table of values and combine it with this feature of the domain. Finding the domain in the range is quite difficult, but I would use a table of values approach to do that and simply start plugging in points and taking a look and seeing how the domain and range are affected by those points. We'll definitely get some practice with that. I'm not going to show you an example. It's fairly straightforward if you use a table of values approach to see what the change of f of x to square root or nth root of f of x is. Okay, we'll see you in class.